Hey crew, welcome back to my channel. So today is actually a math day. Today we are going to be doing the first day in the second unit of BC Calculus. I did not record or film the first unit of calculus, which was derivatives. So this is basing off of the knowledge that you guys may have some, fundamental skills about derivatives. If not, don't worry, I strongly recommend just watching some preliminary videos on how to do derivatives, but this is jumping right into unit 2. So this unit is on applications of the derivative. So specifically this lesson is on critical numbers, increasing and decreasing functions, and the first derivative test. So without further ado, let's get started. So the idea with this day is about where f prime x is 0. So this was sort of covered in derivatives 1, but we talked about a lot how at points, as you can see right here, when the original function goes flat for a minute, for example at the top of a parabola, f prime x is 0 because the slope of the tangent line, if there were like a bunch of tangent lines sort of like going up, which are all, each of these, imagine they were all lines, I know my drawing is not perfect, would be the derivative at that moment. So the derivative at this moment would be 0. So any flat points, the derivative is 0. But of course, we also discussed that it can be undefined. So as you can see up here, this is sort of like when we did the absolute value one, if you remember from derivatives, how it comes like that, about how it can also be undefined at that specific moment because it's a really fast change. So if it has like a cusp like this, where it has having a fast change, or if it flattens out, we talked about how their f of x is either 0 or undefined. So that concept of x being 0 or undefined is really important. Sorry, not x, dy dx, the derivative f prime x, being 0 or undefined is really important because those are critical values. So we're going to talk about that. That should be new. So for example, if you have a function like this, we did find the x and y intercept at the very beginning, but for this, the new part of this lesson is focusing on down here. So if you take the derivative of this function, you get 3x squared minus 6x, right? So you're basically wondering, you're only trying to find the critical values here. You're like, okay, so when is this going to be equal to 0 or undefined? So you know what this looks like, right? This is a parabola. This is not going to be undefined anywhere. So the only thing you have to set it equal to is 0. So you set it equal to 0 and you solve by factoring. And see, I made a little note here about how it's never undefined. Well, it's not linear. Ignore that. But about how it's never undefined. So then you're going to get these two values. You get the x is 2, x is 0, and x is 2. So now we're going to do something called a first derivative number line. Also, if some of this does not quite make sense, I promise it will more in the context of problems. This is just sort of how the order of learning it goes. So we're going to talk about what a first derivative number line is. So you're going to make a line like this in your notebook, where below the line you have x. So these are your different x values. So on here, you're going to plot critical values. It is important to note, although we'll get into this more later, that actually, we're going to get into that later. I lied. So here it's important, you have to write down the critical values. So you want to write 0 and 2 in this case, because we found that these are critical values over here. And this is going to basically break up your number line. So I'm actually not a very big fan of number lines. I really didn't like number lines in like middle school and stuff, but I promise this is really not like that. So just bear with me. So here we have 0 and 2, as there's two spots, right? And we basically want to talk about what the sign of f prime x is doing around those points. The reason that we want to talk about that is because f prime x reflects the slope of the original function. So if we can basically plot what's happening to the slope of the original function around these two x values, that really helps us understand what the graph looks like, the original graph, f of x. So basically, to do this part, you're literally just plugging in points. So you're like, okay, this x is, by the way, like a key. It's not part of the line. So you're like, okay, any number below 0. So you could, for example, pick -1. And then you want to plug it back in to your derivative expression. Not set equal, you want to plug back into your derivative expression, not set equal to 0, obviously. You just want to plug back into what dy dx is, because what you're asking here is, okay, wait, I want to know below x is 0, or rather to the left of x is 0, what is the slope, what is happening to my original function, what is the slope of my original function, which is the same thing as asking, is the derivative positive or negative? Because remember, if the derivative is above this x-axis, if it's positive, that means that the slope of the original graph is increasing. And if the derivative is below, if it's below this x-axis, that means that the slope of the original thing is decreasing. So you're basically saying, if I plug in a value here, will I get a positive or negative number here? So you plug in -1, for example, and here you get a positive number. And then you would plug in 1 in between this interval, and you get a negative. You plug in between this interval, and you get a 2. So it's really, really important to do all of those things. So once you've plugged in these things, you can now tell, as I was saying before, this top line, if I were to have labeled it correctly, would be f of x. So here I say f of x is increasing, f of x is decreasing, f of x is increasing, right? So those are that's just really important information to have. Now, this information will likely, I don't know about your class, in my class, my teacher does ask for us to do this, but in many classes, they won't ask for this directly, but rather for a question that can be most easily answered by using this. So that question is often, across what intervals is f of x increasing or decreasing? So let's answer that question. So using that information, we can answer that question here. So we know that f is increasing on negative infinity to 0 and across 2 to infinity, because we know that f prime x is going to be positive across all of those points. It's always positive. So the function is always increasing. And we know, on the other hand, that f of x is going to be decreasing only across 0 to 2, since f prime of x is going to be negative across those intervals. And by those, I mean that. It's also important to note the open brackets here. I do know that some teachers have people do it differently, so you can ask your teacher about this if you would like to clarify. My teacher told us to always use open brackets, just because that doesn't really cause any problems if you use open brackets, because technically at those exact moments, as we discussed, the derivative here is actually 0. One can't say that it's increasing or decreasing, it's just 0 there, you know what I mean? So yeah, that's just a note about why I use the open brackets, but you should confirm with your teacher that that's what they want you to do. So another thing that's super important that you can do from this information, and this is kind of the last big thing that you can do from this critical value situation, or at least that we've learned on this day, is that you can find the relative minimums and maximums. So what is a relative minimum and maximum? What a great question. So a relative minimum and maximum describes, it's kind of exactly what it sounds like. So for example, on this little graph, you see how they go off to infinity, right? But a relative minimum and relative maximum is going to be something where the slope has just changed and it's temporarily leveled out and hit 0. So do you see how the derivative, and by it, I'm talking about the slope. I'm almost talking about the slope here, but I'll try to be more clear. So here, as you can see, we're going up and up. The slope is positive. For a second here, the slope hits 0, and then the slope is negative. So that sign change of the slope, positive to negative in this case, indicates a maximum. And negative to positive, of course, would indicate a minimum, because here it's going to negative and then positive. And it's also important that at that exact point, f prime of x is 0, or from C, whatever, is 0. And also, one more thing about this, I do think that this should make sense, but this obviously does not work if the original function is not continuous across that. So if you have a hole right here, this is not a relative maximum, because it simply doesn't exist here. Yes, the limit exists, but this is not a limit situation. This is just asking about the value. So this can't be a relative maximum if the value simply does not exist. So that is really important. So the way that you write this actually is quite formal. It is one of those things like proofs where the language really does matter. So you want to say something like relative max of f of is going to be, so remember how we said 0? So now you're going to take this value that you did back here. These are your critical values. You put them on the number line, and so here, let's go back, sorry. So you take your original function, you take the derivative, you get the critical values, and you use those in many ways. One is for a number line, which is really ultimately used for 2, which is writing where the function is increasing or decreasing. And then the third use is finding the relative minimums and maximums. So, sorry about any background noise, by the way, but so the minimums or maximums here. So f of 0, we said of 0. So here you're going to plug it back into the original function, because you're saying at this x value 0, what is the y? They literally are just asking where the relative minimum and maximum is. This is the graph of f of x, not f prime x, not f double prime x. This is just f of x. So they want to know, at this x value, what's the y? So you plug it back in. So you get x is 0. So if you plug y back in, you're going to get 2. Sorry, I'm late. I didn't want to do it again, but you obviously could. So that's going to be relative max. And here you have to write it like this. You're going to write f of 0 is 2 is relative max, since f prime of 0 is 0, really important, like I said, that this top point exists, and because f prime of changes from positive to negative at x equals 0. Similarly, for f of 2, you would plug in, you get negative 2. It's a relative minimum since it equals 0, and since f prime x changes from positive to negative at x equals 2. So that is the idea of the 3 things that you sort of get out of these critical values and using the first derivative. I would just briefly like to note some exceptions. So, not exceptions, rather just sort of things to be aware of. So, these are examples of where f prime of c is 0, but it isn't a relative maximum or minimum. So, that can happen in these 2 situations. For example, here, of course, it is 0, right? I mean, it's going to be 0 all along. But it's not a relative minimum or maximum simply because it's the same slope the entire time. And here is a really important distinction, because this can trip up a lot of people, because it does look like it is flat for a minute. And it is. But the slope here is actually not changing. The slope is positive the whole time. The idea of a slope change, so being like this or like this, is super important. And here the slope doesn't actually change. It's just positive to positive, which you can see quite easily when you graph your first derivative number line. Lastly, there is an important idea here that something can be both a relative extrema and a global maximum or minimum. So relative extrema and a global extrema. So that just means the overall peak. So for example, if I had a function that was this is relative and this is maximum, but this is actually also relative. It's relative and max. So that's just an important note. If your teacher were to ask you which one is relative and maximum, you can note the maximum as also a relative. Okay, so I did actually already complete this homework, but we are now going to go through it just to explain some important notes. So first I just made this little box that I do want to highlight, which is the relative extrema criteria. Sorry if this is messy. So function must be defined, as we talked about. It also must be continuous, as we talked about. This means that, like, even if it's defined, it can't all of a sudden jump up here, you see? Because then it's not a relative, even if it looked better than that, even if it was like that doesn't matter, it doesn't count. Because it is not continuous at that point. So like a jump discontinuity or something like that would do that. It must have a delta slope is what this says, so a change in slope, which you figure out from f prime x. And it must be a critical point. So a critical point, of course, kind of implies this because, actually, that's not true. I take that back completely. Yes, these are separate things. It must be a change in slope, which you find from f prime x, and it must be a critical point, which you find from the zeros or the undefinedness of f prime x. Also, this is a really important note, which is that not all critical points are extremum. So you can have a critical point that isn't, which we kind of talked about before. Here, for example, like this is a critical point, but it is not an extrema because the slope does not change. So problem 1 here asks you, you can't see the packet in front of me, but I'm looking at it, and it asks you to find the x and y intercepts, to find the critical points, to find all intervals where f of x is increasing or decreasing, and then to find the relative extrema and justify your answers. So first we did x and y. I'm not going to go over those because I believe that you all know how to do that, so we're not going to focus on that. Instead, we're going to jump right down to b, which asks about the critical points. So this is the original one. Now, when I say something like this, if you feel really inclined to use the quotient rule here to find the derivative, you can, but would just like to say that it's much easier to make this 8 times x squared minus 1 to the negative 1 and solve like that using the chain rule instead. So that is what I did. So you have to be careful. Remember your chain rule here. You get the derivative, and then you have to set it equal to 0, right? So here's an important note, actually. When you're setting it equal to 0, you're like, okay, so if this equals 0, think logically about this. For this to equal 0, the numerator has to be 0, right? Because if the denominator is 0, it would be undefined. So the numerator being 0 is going to be 16x equals 0, negative 16x equals 0, so x equals 0. So we get that, right? And also, we would solve this. So x squared minus 1 squared is 0. And then x is going to equal plus or minus 1. But this is not a critical point because it is not defined in the original function either. And when you have an undefined thing like this, like when the original function is undefined at a certain place, the derivative is also undefined at that certain place. So, as you can see. So, this is actually an asymptote. Your asymptotes, I did not do this. Actually, I did do this. What am I saying? I thought I did this wrong, but I did not. You have to put your asymptotes. This is really important. I think I'm going to have a note about this later. Yes, I do, which is that when you draw first derivative number line, you must show the vertical asymptotes, which I wrote undefined for f prime x and for f of x. So that's another important thing. I think I just said this, but in case it wasn't clear, if it's undefined for f of x, it's going to be undefined for f prime x. So you must show the vertical asymptotes, even though they're not critical points. And that's because the slope can absolutely change around them. So it is really, sorry, it's messy. It's really important that you do that. So now you want to plot your points. You're going to plot 0, 1, and negative 1 on the x. Then you're going to draw in for f prime x. So again, I wrote no, but you could write something else here if you wanted to. And then you have 0 here. I plugged in around it, and then I can see here that f of x is going to increase, increase, decrease, decrease. This is just helpful information if you were to be graphing it. But it's also helpful to the next part, which is what C actually asks. So this is actually not part of the question. Again, like I was telling you guys before, how can just sort of be useful for you. This is not a question. No question asks this. It just asks you to find all the intervals where f of x is increasing or decreasing, and this helps me with that. So then I can say f of x is increasing across negative infinity to negative 1 or negative 1 to 0. This should be an open bracket. Because f prime x is positive there, it is decreasing across this, hence f prime x is negative there. And then D asks about relative maximum or minimum. So here we can say f of 0 equals negative 8 is a relative maximum since f prime 0 is 0 and f of x changes from positive to negative across that point. So that is just sort of this is a very classic type of problem where it asks you for all of these things and you can use whatever technique you want, but it is recommended to use the number line technique. 2, it was asking the exact same question, as was 3, as was 4, so I will not go over those. And in case you're wondering what the purple is, that's what I usually do my corrections in, and so I did make some mistakes, but because my mistakes were more related to confusions and prior knowledge I had and less into the specific day, I'm not going to go over them right now. So instead, let's move on to question 5. Question 5 is important. So question 5 actually did have a graph of the derivative next to it, which you cannot see here. So yeah, you cannot quite see that, but it does ask where f is increasing. And remember that it's confusing because this graph is actually of the first derivative. Here, I'll try to sketch it for you guys right now. It looks something actually a lot like this. So it asks you where the first derivative is increasing. Oh my goodness. It asks where f is increasing, the normal function f. And it's important to remember that that's actually not where the slope of this is positive. It's where it's just above the x-axis. So this region and this region, one would say. Sorry, I got cut off. Let me redraw this graph for you. So the graph looks again something like this, and again, this value is -2 and this value is 3. So again, it asks where it has relative maximum and minimum. You have to be so careful here. This is a trick question because it looks like it's going to be these 3 points, but remember that this is a graph of f prime x, not f of x. So it's actually when the slope of f prime x, it describes remember how we did it with like the signs of the derivative? So the signs of the first derivative are going from positive to negative or negative to positive is where it is. So that sign change is actually here. It's actually -1 and -2 and at 3. So you have to be really careful not to fall into the trap of looking at the basically flat points of the first derivative. Instead, you're talking about the original one. So you're talking about where the sign changes, where it would go from up to down and have a flat point there is going to be here. And at this spot, mind you, it does hit the x-axis, which just means that it was flat originally. But what's important to know is that this is not an extrema because the slope doesn't change. The slope of the derivative changes, but the slope of the original one doesn't because it's negative the entire time. So we're going to move on to question 6, which says find the value of k such that y equals x over x squared plus k will have a relative extremum at 2.5, and then it asks if it has a maximum or minimum. So I rewrote this as x squared plus k to the -1 times x, and then I found the derivative. So what's important here is that when you finally get to this point eventually, the idea is that you have to set this to 0 because it's telling you that there's a relative extremum there, and a relative extremum comes from, of course, having set the derivative to 0 and finding the basically critical values. So you find the critical values. I did not simplify, but this is obviously just -k squared. So I set this to 0 first, right? And then I'm like, okay, well, for x to be relative to anything, it must be a critical point too, which is the logic behind doing this. Otherwise, I wouldn't care about this. But I'm saying if x is a relative to anything, which we know it is, then it has to be a critical point. So here I want to solve for what this would be. So I happen to know because it literally tells me at x equals 2.5. So if x equals 2.5, then you find that k equals 6.25 eventually. Now note also, I wrote that I could set this equal to 0, but to find the undefined one, because remember, I don't know if I said this already, but setting the denominator equal to 0 will of course get the undefined values, but I already know that it's undefined on the original function. I already know that it's a vertical asymptote because it was like this originally, right? We see this here and we see this here. So even though setting this to 0 just setting the numerator equal to 0 gets you where f prime x is 0. This one gets you f prime x is undefined, which can also be valuable information, except we do actually already know that. So you get that this is the value for k, and you can also note that x is 2.5 and -2.5 because x squared is 6.25 because it said that it is the. So to be thorough, you could put them all around. So I did. Then you test points and you end up getting that f of 2.5 is 0.2, and you get that it's a maximum because f prime x goes from positive to negative there. So you do have to be two things. One is that you do have to, the question at the end ultimately does ask if the point is a relative maximum or minimum, which is why you have to do the number line to help you see. And also you might know that this saying f of 2.5 equals 0.2 is a relative maximum because this goes to positive negative at f.2.5 equals 0 is a little bit different from over here. But either one is fine because they are fundamentally the same thing. So this one asks about a polynomial that has a maximum here and a relative minimum here and another maximum here. And the question, it has no other critical points. How many zeros does it have? So if it tells you that, you should probably graph those. So this is what happens when you graph them. And you know that this one's a maximum, so you know that, and this is, again, the graph of is p of x in this case, but it's the original one. It's no derivative. It has to go from positive to negative because it's a maximum, then negative to positive, then positive to negative. So once you've done that, if it has no other critical points, and then they're just going to continue. No other critical points basically here, no other critical points other than these like minimums or maximums, means that it's not going to have, it doesn't have another minimum or maximum, so it can't turn around. The slope can no longer change. It's stuck going down. So you know that eventually it's going to cross the x-axis. And here, again, it can't change because there's no other point, so it goes straight through. So the question is actually how many zeros there are, how many x-intercepts there are, so you can tell here that there are only going to be 2. Because if there were more, of course, the slope, even if it went through and then changed here, this would be another critical value. So the fact that or a maximum, relative maximum or minimum. So the fact that there are no more means that there are only 2. Okay, so lastly, we are going to do question 9, which does touch on some overarching themes from this day. So it is a really important question. And the last piece of it does touch on stuff that we're going to do tomorrow, which is just second derivative stuff. So this is an important question, but I do recommend that you guys do other practice problems as well. So these are always, sometimes never, a very classic question type. So 9a says, if f prime of 2 is 0, then x equals 2 is a critical number. So this is always true because that's the definition of a critical number. It is not the definition of a relative minimum or maximum, but for a critical number, all it needs to be is the zeros of the derivative. or, of course, when the derivative is undefined. So when the derivative is equal to 0, so when dy dx equals 0, or when dy dx is undefined, is when it is a critical number, a critical point, or critical value. Any of those mean the exact same thing. So this is going to be always. B says, if f prime 2 is 0, sorry, that's A again. If f prime 2 is 0, then there exists a relative extremum on the graph of f of x at x equals 2. So this is the same idea. So we did just say that it's a critical point, right? And it is a critical number. But a relative extrema, as I just said, is a slightly different definition. It has to be a critical point and it also has to change slope from positive to negative or negative to positive, or it has to change slope in some way. The derivative has to change sign. So the original function changes slope. So it has to change slope. So this one, also the idea about being defined is also, of course, true for the first one, but we do know that it's defined across this interval. Well, I guess we don't, but whatever. So if f prime 2 is 0, then it's a critical number. So if f prime 2 is 0, then there exists a relative extrema. That's at x equals 2. That's not always true. That's only sometimes true, right? So C is only true again if the sign changes of the derivative. So C says if there exists a relative extremum on the graph of f of x at x equals 2, then x equals 2 is a critical point. So this is sort of going the other way. It's sort of like the square rectangle thing. So this one is saying that before this one, B was like, if f of x is 2, then there is a relative extrema. And we were like, here it's like, if there's a relative extrema at x equals 2, then x equals 2 is always a critical point. That's true. That's true. Here it's saying if f prime 2 is 0, which would mean if 2 is a critical point. So this is always true because a relative extrema, that's one of the requirements, is that it involves a critical point and sign changing. D says if f prime x is undefined at x equals 2. Sorry, let me just get this exact question up so I'm not miswording it. It says if f prime x is undefined at x equals 2, then x equals 2 is a critical number. So I had written always originally, which has a little bit of a qualification to it. But so this also says CV, which is just critical value. So if f prime x is undefined, then it's a critical number. So this is kind of the same question as 1, right? Except it's a little different. It's about, instead of being 0, it's undefined. So this is always true except if f is not continuous. So I wrote only if f is continuous. If the derivative is undefined at x equals 2, then it could be a critical value. It could look like that originally. But if it's, well, that's not a good example because it's not undefined there, but it could look like that originally, right? But it could also look like this originally. So this is okay because it's defined on the original function even though f prime x is undefined. And in this one, it's not okay because it's not continuous across the original function. It's not defined, yeah? So that's the qualification. And then E, the last one, is sort of about what we'll discuss tomorrow, so don't worry if it doesn't make total sense to you, but it says, suppose f of x is a continuous and differentiable anywhere. If f prime 2 is 0 and f double prime 2 is positive, then there exists a relative minimum of the graph at f of x equals, f of x at x equals 2. So the idea behind this is that they're telling you that it's continuous everywhere. So you have to know what f of x looks like. And then they're telling you that the f prime of 2 is 0 and the f double prime of 2 is positive. So let's just see what that would look like. This is a 2, not squared. So for f of x, we're saying it's continuous everywhere. Something like a parabola would work, right? And we're saying at the point 2, there exists basically a relative minimum. Let's just say for word 1, right? So then f prime x would, of course, look like this. It has to cross here. It has to go from a negative slope to a positive slope, right? So here we're going to go from negative to positive in f prime x with the thing at 2. Then it's telling you f prime x is f double prime of 2 is positive. So is this true? Let's think. So what's the slope doing here? The slope is always increasing, right? So that means that this is not a perfect graph, of course. I did not really think about this. I just made something where it's always in like a positive. It's always above this x-axis line for f double prime of 2. So then this is always true, right? See, I wrote always because the question was if it's continuous, if f is continuous and differentiable everywhere, if f prime 2 is 0, as we show here, and if f double prime 2 is positive, is larger than 0, like positive, then there exists a relative minimum x equals 2. And as we can see that is true. Okay, I'm just here writing thank you because I really hope that you guys enjoyed this video. I hope this helped clear things up about this day, or just that learning with me was a good experience. I know sometimes it feels like everyone you learn from is like so knowledgeable and perfect about everything and like understands it all, and obviously that can be a really great thing, but it can also be nice sometimes to learn with people who are learning with you and who don't know everything perfectly and who are figuring it out, just because the way their mind works can be a little bit more relatable and more like, oh, I get it, and the figuring out process is going to be more together. So I really hope it does feel like we're working together, because that's my ultimate priority. And if you do have any questions, drop them down in the comments, and I will answer them in the next video. Have a good night. Bye, crew.